if you remember, one day that is we started this topic, that is operation on system interconnections, right? Because many places you will find that you will have to handle the interconnections. Like one is G2, G1 or G1, G2. There is a cascade or series. Sometimes it may be completely a parallel interconnection. Okay, so that representation will be G2 plus G1. Then the longest derivation which we are now going to do, that is longest in the sense among all of them, that is the feedback interconnection. Why that is longest? Because there you have to find out the representation of I plus G2 G1 whole inverse into G2. Either this one or I plus G1 G2 whole inverse into G1. Okay, especially like this will be the interconnection if you consider Y1 to be the output. And this one, if you consider Y2 to be the final output. Okay. Then after that is we will also try to find out, that is if you have, this is what I am now going to write, this is what adjoint of a system. Maybe this is new to you, or even you might have heard about the term adjoint in linear system theory, but adjoint, what is adjoint system? It's state-based representation that we will learn. Okay, so this is called adjoint. Today, that is already we have done the first two. Today, that is this is going to be done, and then on another day, that is we will learn the other two. One is adjoint, another one is the inverse. All of them, they are, that is in some of the applications or in some situations you will find that is you have to work with this state-based representation of this kind of system interconnection. Okay, so that's why that is ready. That is in the beginning I said that is the not only the mathematical prerequisites about this kind of system operations which are the part of multivariable control theory, those should also be known to us. Otherwise what will happen, that is in robust control, many places you will feel as if handicapped. That means if we are not known to all the tools and the other prerequisite, then what will happen, that is that quite often you will feel that is okay, these things is required to be done, but I don't know how to do it. Specifically that, so what the situation, suppose when we learn the robust controller synthesis algorithms as an uncertainty modeling, many other cases, you will have to handle multivariable system. They are quite often you will be handling, or that you will encounter this kind of system interconnection. So if you don't know that is how to find out their state-based representation, then anyway, only for that small bit that is you will get stuck. So that's why that is like this year, that is compared to like last year, this year that I have streamlined the subject even in a better way. So as if you see the flow, that is subsequently that is we are progressing, right? So I haven't yet like started the core of the robust control, because the basics of robust control is nothing but the multivariable system theory. Whatever that is we are learning, these things would be highly required when we will delve into the real robust control. Okay, but these things I could have completely like skipped, and that is I could have left all these things to you. But in that case, it would have been a great burden for all of you, right? Because then there is all these things that is you will have to learn from any of the multivariable control book or other ways. So that will definitely need further time, and as well as that is your not only time, that is your effort, energy, and sometimes understanding from the book. That is also not very easy. Say for example, if you see Kemichow's book or even this Skogestad as well, the derivation which here we have done, especially that is last day you have seen we derived the state-based representation of the cascade and the parallel. Parallel is really easy, but even cascade and this one specially, in the book they don't show you the full derivation. You check Kemichow's book, even the other one, They will only show that is okay, if you have an interconnection or if you have a cascade, this will be the final state space representation. But in between, that is the steps, how it is going, from where we are doing the simplification, all those things are completely absent. That is the reason, that is why I am like specifically taking up all the things one, although it is like killing the time, or rather I should not say killing, because this is also like quite good learning. But anyway, that is, if I would have skipped, then I would have been able to cover many other things from robust control. But in that case, it might be difficult for you to get into all those things. So that is the reason why I am doing everything here. Okay. So I believe the flow and the content is fine for all of you. We were learning well. Later we have to gradually raise our speed. So that is the reason why there is for both the subjects, robust and nonlinear, initially I am going slow because both the things are new to you. Anyways, this is now this one of the like, most important exercise for us to find out the closed loop state space matrices for a feedback interconnection. Okay. We have already done that for cascade or series and parallel. So you have already learned that is how to do, right? So that means the replacement or substitution of some of the variables by some other variables, that knowledge you have already gathered. So here also, that is when if somebody asks you that what will be the representation, then it is like you have one plant and you have one controller. Just to, in the CISO case, suppose in the CISO case, if you have G1 and G2, then simply like G1 by 1 plus G1, G2. If somebody asks you what will be the state space for that, exactly the same problem. But for MIMO, we cannot simply write something by something or 1 plus G1, G2, right? Because it's a matrix. So that is the reason, that is why formally we have to learn especially about the matrix multiplication, inverse and all that thing. Okay? In between, that is, we will use one matrix operation called the push through rule. Only that is unknown to you so to date, I believe. There is one rule called push through rule. We will learn this. We will learn that today. Don't worry. So at this moment, can anybody tell me that is what I should do? I hope you have understood the problem, that is what needs to be done. That is, we have to find out this ACL, PCL, CCL and DCL, right? So for that, how should we approach? Like that day, here also we are going to have a combined state vector x, which will be x1 and x2. So one of the expression, that is, this means, that is the capital X dot, that means x1 dot, x2 dot, that is equals to ACL x plus BCL W, right? You can ask that is, sir, why you haven't written U1 and U2? Because they will be embedded, right? It's an interconnection, so anyway they would be embedded. So here we can expect the exogenous signal. So W means W1 and W2. Similarly, if I consider Y1 to be the output of Y, then it will have CCL X plus DCL W. So this is the thing that is which I need. Suppose here that this one I am referring to by GCL. So that is the thing which we need. Okay. Is it now clear to all of you? If it is so, then exactly in the same way we have to find out x1 dot, x2 dot. But only one difficulty you will face. That is in x1 dot, of course, this u1 has to be replaced. What is your u1? U1 is w1 minus y2. Y2 means again this one. Here in turn U2 is appearing. Again U2 means Y1 plus W2. So that's why it is a coupled thing. Right? And that's why that is for all beginners we like tend to be in a loop. That is, if it depends upon U1, then U1 means Y1 minus W2. Sorry, W1 minus Y2. Again Y2 means this equation. Here we are going to have U2. And then U2 means my Y1 and W2. So in that way you may may fall into a loop. That is how can we resolve, right? But exactly the same way which we did last day, that today also we will do it accordingly. Okay. So like let's try to find out y1 and y2 independently. That means here you have this y1, here u2. That is, if I ask you, that is, try to represent y1 and y2 in terms of x1, x2, w1, w2. Can you do that? That is, finally whatever equations you will have to find, we have to completely eliminate u1 and u2. So if I now ask you that find y1 and y2 as a function of w1, w2, x1 and x2, can you do it? Is it fine for all of you? Just please look at the board. The moment you reach up to the third step, Nidisha, please. The moment you reach up to third step, then you carefully look at the terms. x1, x2, you check with that of what I said. That is, I wish to express y1 and y2 in terms of w1, w2, x1, x2. So at this moment, what is the situation? x1, x2, and then here we are easily getting w1, here another w1, but so far we don't have w2. That is fine, but at this moment here we have one y1 term. Don't worry, you are starting with y1. Immediately that should strike you, that is okay. If I put that term in the left hand side, immediately that will give me I plus d1, d2. In other case, you will find I plus d2, d1, and then finally it would come as an inverse on the right hand side, I plus d2, d1 whole inverse. And this time also, well-posedness must be the prerequisite, so I plus d2, d1 whole inverse should exist according to the well-posedness assumption. That is the trick. You should not be afraid, we have so many terms, how to handle. It is not. Everything are falling on place. Are you understanding what I said? बोलो क्या समस्या हुआ? Nitisha, is it fine or not? ठीक है. Take your time and think, because it is not that is I am doing a like 20 lines derivation and you will be just getting that by heart. That shouldn't be. We all should be able to understand the way I am proceeding. That is, what is the logic behind that. It is not only simply line by line derivation. It is not at all. In fact, this is not a derivation. It is only, that is, algebraic simplification, right? We are like here handling some matrices and signals that has some specific pattern, and the simplification also has certain points, by following which I am writing in a particular way. It is not that all of a sudden we are like starting some equation and then you will be replacing one by one. It is not. Whatever may be for any of the control subject, that is, we should always first think what needs to be done. Okay, that is the first thing. Second, what are the things given? Third, what techniques you know. this thing for any mathematical subject, these steps are highly important. Once again, first step is what needs to be proved or what needs to be done. Second, what are the given things. Third, what are the techniques known to you, and then you start. It is not that like the moment you have got the question or whatever problem statement, you immediately start writing. In that way, you will lose the flow. And there, that is even after proceeding to some extent, you will find, I am completely stuck or I am in a deadlock. I don't know how to proceed further. So always, that is, if you have seen the sequence with which I am now proceeding, it has a clear-cut objective, and the technique also which I am going to use exactly falling with this, right? Aritra, for all of you, Kanika, is it now fine?
So should it be that d1 d2 should be d1 d2 multiplied by w2 plus y1?
Yes. It's just a mistake, time. Thank you. So here it is like an algebraic loop kind of situation. That is, in the left hand side you have a y1 term, in the right hand side also you have a y1 term, but you should not be afraid of. Why? Because we are going to bring that term in the left hand side, and immediately it will give you I plus d to d1, right? That is, after this, what should I write? That is I plus d1 d2, and then y1. Here also you must be careful that y1 is a vector, so it will always be on the right side. In no way we can write y1 into I plus d1 d2, okay? That is a completely mistake, okay? So that is equals to c1 x1 minus d1 c2 x2. What are the remaining terms? Plus d1 w1 minus d1 d2 w2. Is it fine? Please check whether I made any mistake. Then your y1 equals to I plus d1 d2 whole inverse. Everything will remain as it is, c1 x1 d1 c2 x2. We need further simplification, but not exactly at this moment. When it will plug in other equations, then we will need to do some further simplification, but at this moment you can keep it as it is, okay? Plus d1 w1 minus d1 d2 w2. Is it fine for all of you? Did I do any mistake? Please always check. I hope this is fine up to this much. Similarly, we have to find that of y2, okay? Because those things we will be needing. You can answer, sir, why you are doing it beforehand? Because you think about, that is, we have to express y1, sorry, x1 dot and then x2 dot. So anyway, there is inevitably in x1 dot you will have to deal with u1. u1 means w1 minus y2. So we will be needing y2. Similarly here, u2, which is equals to w2 plus y1, you would be needing y1. Have you understood what did I say? That is, your finally x dot equals to ACL x, right? X dot means x1 dot x2 dot. So this one will have to simplify, this one will have to simplify. Why? Because this u1, that is my w1 minus y2, W1 is independent, exogenous signal, no problem with that. But immediately Y2 will come. So we need a compact expression for Y2. As we have done for Y1, that's why we need for Y2 as well. Here, x2 dot e2 x2 plus b2 u2. U2 means W2 plus Y1. So actually this is the reason why I started this. Is it now clear? That is why beforehand I have started working with Y1 and now I have asked you to find Y2. This is the reason. Okay, so let's find Y2. Now I hope the flow is known to all of you, right? Y2 we can find. So C2 x2 plus D2 u2 equals to C2 x2 plus D2 u2 means y1 plus w2. Find C2 x2 plus D2. Now your y1. Y1 means that is you have a very long expression, right? Just to save some space, we would use two shorthand notations: U for I plus D1, I plus D1, D2, and V for I plus D2, D1. Okay. So now that is D2 into Y1. You have already, that is you have Y1. So it is going to be U inverse, right? U inverse. Then D2 into U inverse. Tell me one by one. That is C1 x1 minus D1 C2 x2
D1 W1
exactly.
minus D1 D2 W2.
Thank you. So that is fine up to this much, and you have the remaining term D2 W2, isn't it? Right? C2 x2. Here you have another x2 term is going to come, so that would be D2 U inverse. It will be minus, right? D2 U inverse D1 C2 x2 plus you have the x1 term D2 U inverse C1 x1 plus D2 D1. You should have D2 U inverse D1 W1 minus D2 U inverse D1 D2 W2 plus D2 W2. Please check whether I made any mistake. All of you, please look at the board and check whether I have correctly written on the terms in the last expression. Don't worry, we will check the proof as well. This is called push-through rule. Can anybody tell me why the name has been given push-through?
AM has been pushed through.
Exactly, very good. Like, as if this guy is here, that is, he is trying to get inside, and when he is, all of you please look at the board, that is, what is the meaning of this push-through rule? As if, how many of you have boarded metro rail? You? All of you? मेट्रो रेल में क्या होता है? हम लोग इंडिया में बहुत क्राउडेड होता है ना, जब भी कोई स्टेशन आता है लोग घुसने के लिए क्या करता है? इधर भी वही एग्जैक्टली सेम है। ये देखो, एम अंदर घुसने का कोशिश कर रहा है, इधर बैठने का जगह सिर्फ दोनों का ही है, तो किसको हटाएगा? इसको, तो वही ये बाहर चला जाएगा।
Is it like A, B and C, then A enters and C and go outside?
Something like that. Only thing that is here, if you ask me, that is what about the dimension? This M and N, they must be matrix product compatible, matrix multiplication compatible. Okay, that is about the dimension. Well, we will see that is how the proof can be done. Okay, but this is one of the very handy matrix theory or like matrix algebra identity by which we can do a lot of simplification. Here we are going to use this push-through rule extensively.
So in this derivation, if we don't introduce the y1 directly, it would be much easier to derive.
Is it?
Yeah, because I already derived it and it seems it looks like V inverse into d2 c1 x1 plus c2 x2 plus d2 d1 w1 plus d2 w2.
That is, here you were saying that is with y1, but anyway this is going to come after that. That is, you were saying that is I don't have to
Introduce that u inverse the whole thing. Instead of that, we just put y1 equal to c1 x1 plus d1.
At this moment, that is it. Same. That is for only for y2. You have seen that is it is giving you some advantage. But anyway, that is we will finally put the terms over there. In some places, you have to do this simplification. Okay. So that is as of now. Here, could you see that is whether I have missed any term? Please check this side. That is by the time that is I am doing this one. Okay. That is I minus d2 I plus d1 d2 whole inverse into d1. That is I am individually showing the terms. Okay. Then that is you will understand that is how the push-through rule is we are using. So I hope you have also got the term, right?
Yeah.
V inverse C2x2.
V inverse C2x2.
Have you understood? That is how I have applied the push through rule. This is very important. Nitisha, please check it correctly. Okay? So now this will be the term for what did we get? V inverse. That means I plus d to d1 whole inverse into C2x2. This is one of the term. Then d2 u inverse C1 x1. We don't have any other term for x1, so that no simplification is expected at this moment. Okay. For w1, of course, we need some simplification. I'm going to do it. And d2 w2. That is also fine. Now we have to check, that is what is our situation here. So that's what I was thinking about. That is how the things is going on.
Can we take D2 u inverse D1 W1 outside, then I minus D2 by D2 W2 by W1 into W? But if we
Just a second. I made the mistake because I thought, yes, it was my mistake only. Why? Because I considered this one to be just that I thought this is also W1. So that's why I was trying to take common. But anyway, when I'm doing the calculation mentally, I'm not able to simplify it. So just now that is I marked. So W2 has to be paired with W2 term. Actually, that is by mistake I was thinking about taking this W1 and W2. Yes, that is fine. See, this is also a good exercise for you. Why? Because anybody, that is we all human beings, that is we are prone to make mistake. But you may make a mistake, but at the same time you must be able to detect the error. See, the moment that is I wrote, that is it was like by mistake, that is I was trying to club these two terms and I read this one to be W1, then but immediately I stopped. That is why there is a good exercise or is a good observation for you, because when you will be doing lengthy derivation, quite often this type of situation will arise. But so that's why that is I repeatedly suggest my students, that is when you do something, please don't do it blindly. That is after doing every step, you think about that is what you have done, whether that is correct or not. Here you might have seen, that is when that is I started simplifying this side, I kept that one as it is. Why? Because when mentally I was checking the derivation, I was not able to simplify like this one. So that's why I could immediately detect I myself might have made a mistake. That's why I kept this as it is for later and I concentrated on the other part, that is which already this mentally I could do. All of you should follow that one. That is when in a long derivation, if that is what either you are doing or you are checking from a paper, every time that is you must be careful about that when you are moving to one step from the other, what is the thing you have done, whether that is correct or not. Please don't do it blindly, because then what will happen, that is after doing maybe 10, 20 or 30 lines of thing, or maybe after spending a few days, you will find, array, initially I made a blunder and my entire time is a waste. That's why that is we should be careful in doing long derivations. Okay. So now I think that is fine. So it is d2 u inverse d1 w1. Or can we simplify this further? By using push through rule, we can do it, right? So let me do it for d2. So if I take d2 w2, I can take from here. There is another thing is that d2 you can take common either from left side but from right side as well. Both the things will work. Okay. Let me take common from the right hand side. If I do it, so this d2 and d2w2, I'm going to take it common, right? So if it is so, then what will be the term? That is I minus d2 u inverse d1, and then in the right side it will be d2w2. I hope this is fine for all of you. want this one to be V inverse
I
D2.
want V inverse D2W2.
Check this term, that is, this is coming, right? There is D2 U inverse D1 W1. This is a whole term. Please check whether there is I made any mistake.
Yeah, it's fine. It's fine. It's fine. It's fine.
Fine. Nidisha, you also check. All of you. Sudarshan, is it going fine? So then this one, actually both of them are equivalent. This D2 into U inverse D1 W1 is exactly same as V inverse D2 D1. Okay, the same thing. It is just because of the Puster rule. Now this one will have to simplify exactly in the same way. I am going to simplify. How? This one have you understood? ये जो D2 इसको थोड़ा धक्का मार के इधर से बाहर कर दिया and then everything remaining follows. Okay? इधर भी अभी same होने वाला है. Could you that is here actually I don't have space, so that's why I'm not able to write all the terms. All of you please look into this, take your time, no hurry. Then y2, please sum up the terms starting from d2 u inverse c1 x1. d2 u inverse c1 x1, right? Plus v inverse c2 x2 plus v inverse c2 x2. Is it fine? Or if it doesn't match, please tell me. Okay. Then after that we need a w1 term. So W1 term is going to be, that is V inverse D2 D1 W1. You can write the other one as well, like D2 U inverse D1 W1, exactly the same thing. Okay. And plus W2 term is remaining. That is going to be my V inverse D2 W2. V inverse D2 W2. All of you, please check the whole derivation, whatever we have done so far. Everyone should agree. Then that is we will proceed to the next stuff.
Shouldn't be there one more V inverse term instead of U inverse? U inverse that we can simplify, right?
D2 you.
Yeah.
That is not actually simplifying. It is the same thing that is
Yeah.
there. It was in terms of you would have done in terms of he. Yes, that is also possible. Good. Why not? So here D2 you inverse means that is I plus D1 D2 whole inverse, right? C1 X1. Then वही मतलब D2 आके उसको अंदर जाना है. D2 D1 whole inverse, then D2 इधर आ जाएगा. And now that is going to be V inverse D2 C1 X1. Is it fine for all of you? ये पुश रूल लगे बहुत फनी है ना? I hope this is for the first time that is you are doing this long derivation, right? But it will help you later. In reverse control, one of the longest proof we will learn when we will prove the bounded real lemma. And in optimal control, one of the longest proof is that for the Pontryagin minimum principle. When if you do it by using the Hamiltonian, that has a very long. Even LQR proof is also quite long, but the Pontryagin is even longer.
We have also done in BCS class that proof consensus.
Oh, हाँ state feedback consensus, yes. वो खतरनाक था, and especially in your first semester. Now, all of you have already you have learned many things, but in the first semester that is tough. So after that, I hope that is now you are equipped with the tools. That is, we think, or rather, that is, we have done almost 50%. Another 50% means that is, you have to get the expression for x1 dot and x2 dot. Start doing that. I will also do. First of all, you tell me, because I don't have any space. I will have to erase this part. You tell me whether all of you are okay with that. I give you some time more. No hurry. Take your time. किसी को भी अगर कुछ डाउट है तो अभी पूछो. Here I didn't have space, so that's why in the last term and last line I couldn't write D2W2. Here you have D2W2, okay? Manish, is it fine? Fine? Should I start? Okay. You also do it? I will also do it. बोलता था शायद ना? ओ मैं देखकर बोलता. By the way, हिंदी में बोलता को क्या बोलते हैं?
मधुमक्खी ना वो एग्जैक्टली सेम नहीं होता है.
बोलता का इंग्लिश क्या है?
बोलता क्या होता है? वास.
अच्छा हाँ मैं सोचा वही.
वो भी कंट्रोल सीखने
एग्जैक्टली वो देखा ना, वो तो सारी डॉग्स आता है जो उनका नॉलिनिया सीखने का मन है. This x1 dot, would you do it? Come, do it. It will be a good practice for you. Would you? Problem nahi, that is only about that is some of the simplifications you won't be able to do it. Like here, the few of the things were really big. when that is we had two terms and from that we really got a small term, right? That would have been a problem. Okay, tell me that is how now that is it is quite fine. I hope only thing that is we have to do some simplifications. So x1 dot equals to a1 x1 plus b1 that means a1 x1 plus b1. पिक्चर कहाँ गया? ओ मैं खुद ही इरेज कर w1 minus y2. So it is a1 x1 plus b1 and then Aritra, tell me that is here should I directly substitute y2 or that is
I will substitute the y2.
y2, right? So that means that expression. So I'm going to have b1 into 1 by 1 I can write. So first one is v inverse d2 c1 x1. V inverse d2 c1 x1. Then the second one v inverse c2 x2 plus v inverse c2 x2. And after that v inverse d2 d1 w1. V inverse d2 d1 w1 and then v inverse d2 w2 plus v inverse d2 w2. Is it fine? All of you please check whether did I make it mistake. Now I am going to write all the x1 terms together, then x2, after that w1, w2. Now have you seen that is here, that is what I originally wanted to express all these terms, not only y1, y2, if an x1 dot, x2 dot in terms of x1, x2, w1, w2. That means there shouldn't be any u1, u2 terms. So that is really happening. Now you see that is in this expression you don't have any u term nor any y term, right? That is the thing we wanted. So going to be a1 minus b1 v inverse d2 c1 whole thing into x1. Fine. And then you have a x2 term, so that is b1 v inverse c2 x2. x1 and x2. Then we can see we have two w1 terms. That means some further simplification is going to be possible. So the w1 term is b1 w1 and then minus b1 v inverse d2 d1 w1. Yes, we had two w1 terms. How many w2 terms? Only one, right? That is minus b1 v inverse d2 w2. Is it fine up to this much? Now after this, what should I do? Now I have to simplify this, right? The w1 term. Now from which term should I take common? I cannot take b1 w1 common from right hand side, because here in the right hand side the second term doesn't have any b1. So b1 has to be taken from left side, w1 has to be taken from right side, isn't it? Please check whether you are fine with this or not. Can you see properly? Otherwise, you can sit in front. can I directly write this? Please tell me whether you have understood this simplification from this to this. Just you replace V by its original simplification, that is original expansion, that is I plus d2 d1. I means V inverse into V, and then I have taken V inverse common, isn't it? Are you getting or not? Fine? Yeah, not getting. Not getting. ये I का मतलब क्या होता है?
नहीं ये ठीक है इनवर्स d1 को फाइनली v इनवर्स w1 कैसे होगा?
अरे वो तो इधर से
हाँ
V,
हाँ हाँ
ये जो I means this is actually V inverse into V. And then if you take V inverse common, then here it will be V. V means I plus d2 d1, and then that d2 d1 is going to be cancelled with this d2 d1. Is it now fine? ठीक है होगा
जैसे तो होगा बट मेरे दिमाग में आ रहा है सब मैट्रिक्स तो स्क्वायर नहीं है कि हम लोग ऐसे देख के कर देंगे कोई कॉलम वेक्टर है कोई रो वेक्टर है कोई स्क्वायर मैट्रिक्स है कोई रेक्टेंगुलर है मल्टीप्लिकेशन कैसे कैसे हो रहा है
ओके
जैसे हम लोग ABCD तो सब नहीं है ना these are all our matrices and vectors so हम लोगों का डायमेंशन भी तो पता करना है ना ऐसे
Can anybody answer her question?
Like from the first when we write those equations,
Well postness. So when we are like taking that well postness assumption, then first of all the interconnection exists. And even before that, all the dimensionalities that you were thinking about, all of them must be of comfortable dimension. Otherwise, you cannot form the interconnection. And here, as you mentioned that some of them are vectors, some of them matrices. Here, what are the vector terms? Only the rightmost terms are vector. Like here, x1 is a vector, x2 is a vector. Here, similarly, w1, w2.
No, B1 and C1 is B1, C1.
All of them are matrices, no vector. How they can be vector? You think about the ABCD. All of them are.
Column matrix.
It can be column matrix, it can be tall matrix, fat matrix, anyway. But all of them would be matrix dimension compatible. That is the basic assumption, because otherwise you cannot form the interconnection, right? So that is here, if you see, that is all of them one by one, you write down the notation, they have to be, when you are making the interconnection, then only the d2, d1 or d1, d2, all of them should be, that is matrix multiplication compatible. Okay, that is the guarantee. Here, that is whatever simplification or derivation we are doing under that assumption that yes, all of them are the dimension compatibility, all of the dimension compatibilities are there, otherwise we cannot write. And if you see d2, d1 and d1, d2, both of them have to be square matrices. Why? Because otherwise you cannot write I plus d1, d2. When we are writing u and v, so you see in one of them I plus d1, d2, in the other one I plus d2, d1. That is, it is a plus. So of course that is D1, D2 and D2, Dn must be square. Otherwise, because identity matrix cannot be non-square, it would be always square. And here this is an addition or like summation of two matrices. So that is its dimension must be first of all is square, and then they should be of the same dimension. And its inverse exists by the Well-Posnes assumption, okay? And thereafter that, if you decide that is, you might be thinking about that is okay, that is इधर but ये dimension क्या होगा? V1 V inverse D2, then ये जो D1 D2 इधर इसका जो dimension होगा वो B का side जो B का number of columns B1 का, and here U1, and finally if you see the interconnection, then U2 will be going there. So it has to be, that is because you know when you wrote U1 equals to W1 minus Y2. So those vectors should all of same dimension. Then U2 equals to W2 plus Y1. All of those vectors of same dimension. So if you check all those dimensions, finally this will, all of them would be product compatible. Okay, that is the guarantee. So up to that, is this fine? If it is fine, then you please proceed to find out x2 dot. Only the last bit. is expansion, right? Please check. Then similarly we have to do the simplification. I mean not simplification, basically grouping, right? So B2 U inverse C1 X1, that is the first term, and then in bracket you have A2 minus B2 U inverse D1 C2 X2 plus the third term is going to be B2 U inverse D1 W1, which is same as B2 it fine? Now all of you that is in your copy, you finally write down the matrix vector format, okay? That is x1 dot x2 dot, that is equals to this ACL, that means 4 entries into x plus BCL in W1, W2. You write that on your copy. Later it will help you to remember. Finally, what is the thing that we were looking for? That is x dot equals to ACL x plus BCL W. Then y equals to CCL x plus DCL W, right? So what we are looking for, capital X dot, x means x1, x2. That is ACL x plus BCL W, and then y equals to CCL x plus DCL W. So your x is the vector of x1, x2, W is the vector of W1, W2, okay? But y we have considered to be y1. If you see, this is the most generic derivation. Even in the Kemming-Chau's book, they didn't consider the W2. If you see chapter 3 of Keminjo's book, where the final expression is given, they have considered only one exogenous signal, W1. They have written to be R, but W2 they didn't consider. So in that way, that is whatever book you consider, this is the most generic derivation where we have all the terms, both W1, W2, in fact D1, D2. That is, in some books you will find they assume that one of the system is strictly proper. What is the advantage then? This D2, D1 will always be 0. If one of the system is strictly proper, then D2, D1 or D1, D2 will always be 0. So that will significantly simplify or reduce the amount of derivation, right? And similarly, if you consider W2 is 0, I mean one of the exogenous signal is absent, then also you can get rid of some of the terms. But once you learn this, after that you won't have that hesitation in doing a derivation, right? So that is the reason why I did it. Let us take a break and then after that we will start. Okay. All of you please check the whole derivation if you have any. So those things are mostly done. As I said, two more thing is there. One is the state space representation for the adjoint system, another one for the inverse system. That is not required exactly at this moment, but anyway we'll have to learn that. Now I am thinking that is what is the next. Do you have any suggestion? That is like, is there anything left in any of the earlier classes? Please check your notes. Did I mention there is anything to be discussed later? So far, whatever we learn, are they fine to all of us? What more tools do you need? Do we need inverse control? Any suggestion?
Sir, norms.
Norms. Okay. Any other? क्या? No, like norms as a prerequisite that we can discuss. That is not a problem. But anyway, there is uncertainty modeling. That is a big topic. But before the big sim, we will cover the total uncertainty. Okay. But norm. So do all of you be happy if I start the norm? Or any suggestion?
No, H2 norm is what we have.
But other than the matrix norm, vector norm, those things, are they fine or should I discuss? For all of you?
Yes.
And little bit, that is if we revise. I said that is norm, that is first of all now you tell me, that is why do you need norm or what is a norm?
A real number that represents the strength, magnitude, or size of something.
Right, that means essentially it started with the length, right? When we talk about a norm of a vector, it originally started with the length. But not only length, if it is a vector, of course the norm, this norm means that if we have to quantify the length, it would be accordingly the norm would be decided. But if it is a matrix, then for a matrix we cannot directly talk about its length. Then it is about the size, right? So one is length, another is size. Then other than that,
Peak value.
peak value, that we will come later. That means in terms of gain, right? If it is in terms of if it is system, then of course that is in terms of gain, or else energy content. Energy. So these things are about, that is, as you said, the strength of something, right? Strength or power. So we have different type of mathematical objects, maybe starting from vectors, then matrix, then signals, system. Sometimes, although we don't need that much in our study, sequence, right? All of these are different type of mathematical objects, and for all of them, at some point of time, we need to quantify their length or size or their like power. I mean, either the energy content or their gain, something like that. Okay. So for each one of them, we have to define the norm. But the meaning of the norm or the utility for which we are defining, that changes. Like as I said, in case of vector, the norm is it is a kind of length. It is not always the exact length, because when you consider the two norm, that is the exact length. But one norm is also there, infinity norm is also there, right? So, but they also give another type of length. Okay. Similarly for matrix, like different sizes we can talk about. So here also there is, you have a one norm, two norm, and the other kind of norm. Okay. For vector norm is the most straightforward. Matrix norm, it has some other type of things as well. For signals, you have, there is one concept. For systems, you have another one. The sequence also you have something. That is, let us see. That is one by one. Suppose you have a vector, okay, 4 cross 1. If I ask you, there is what is the 2 norm? Actually, if I ask you, there is what is the length, then what would you do? When you suppose, if it is a vector, if why I am just noting a small a, because it's a vector, because usually the convention is the small letter means they are the vectors. If it is capital letter, that means a matrix. Okay. Now for that vector, if I write, that is A, usually this notation, that means this is a norm. Without, if we don't write anything, then the convention is that it is actually the 2 norm, vector 2 norm, right? So that is going to be x1 square, x2 square plus x3 square plus x4 square. This is the standard 2 norm, or exactly the length. We don't have any doubt about it. If it is 1 norm, then
Max.
Absolute.
Absolute.
that is sum of the absolute values. That is 1. So here the general notation is that summation xi square
What?
Only
and that is for the p norm, right?
So then x to the power p will be there.
x to the third, that is here either p belongs to vector p norm. So this is the way of writing all the norms in a consolidated way, and that is the reason why I have put the absolute value. If it is specifically a true norm, as this is a square, you need to separately write that it's a absolute value, right? That is about the thing. So this is about the vector p norm, that it is for all p starting from 1 but infinity is excluded, okay? So for this case, if it is for, in general, what would happen if this is for n? So x1 square, x2 square up to xn square, right? Now if it is 1 now, then what we have to do? So if for this particular case, what will happen? That is x1, x2, x3 plus x4, right? So this is also called sum norm or absolute sum norm. Infinity norm, or also we sometimes call max norm, right? Infinity norm or max norm. Max over I, isn't it? In some books you will find that is instead of maximum they express it in terms of supremum, right? So in that case, like another version, often that is we call sup, that is the supremum by mod of xi. Can anybody tell me that what is the difference between maximum and supremum? That is, at this moment I said that is both of them will give you the same result. That they are at least in vector, of course finite dimensional vector, they will give you the same thing whether you write max or supremum. But they have different, in this case for finite dimensional vectors they will give you the same result. That doesn't mean the maximum and supremum they are the same things. Think and tell me, that is, what is the difference between maximum and supremum?
So maximum will give us the exact vector or whatever quantity we are trying to get the maximum. But when we write supremum, it might indirectly give us the strength, but it will not directly
In
give
the
us
definition there is no change. I am asking mathematically, there is a maximum when you suppose that is you have a set of elements from which over which you can then pick up the maximum one, right? Supremum also we have used in the same meaning, but mathematically they have a subtle difference. What is that? There is no change in the definition of the norm. Okay, I am asking about the maximum or supremum, the definition or their operation.
Maximum eigenvalues के matrix
इसमें
के
eigenvalue को मतलब
otherwise
we are already facing problem, and if you then include some other things, then the situation will be further complicated.
सिंगुलर वैल्यू डिकम्पोजिशन पे कंडीशन को भी आ सकता है और मैक्सिमम
सुप्रीमम के साथ सिंगुलर वैल्यू डिकम्पोजिशन का क्या संबंध है?
एसवीडी कहते हैं ना सिग्मा सिग्मा सुप्रीमम में आता है और मैक्सिमम लैम्डा में मैक्सिमम हो जाएगा ना वो मैट्रिक्स में पर अभी तो वेक्टर के बात हो रहा है
सिंगुलर वैल्यू में वो जो बीच में जो सिग्मा है वो उसको सिंगुलर वैल्यू
So,
सिंगुलर
ये
वैल्यू
condition
के
वही
साथ
condition cross-
सुप्रीमम का कुछ रिलेशन है क्या?
क्योंकि सुप्रीमम में बाद में हम लोग मैट्रिक्स में जब सुप्रीमम लिखेंगे तो उसके टाइम पे हम लोग उसका एसवीडी का सिग्मा को लेके हम लोग उसको
First sigma is the biggest.
बट देयर सिग्मा मैक्स एंड सिग्मा मिन, उधर तो सुप्रीमम का कुछ नहीं था, सुप्रीमम या इंफीमम का कुछ नहीं था,
बाद में हम लोग करेंगे
इसे आज तक मैंने नहीं सुना. Anyway, suppose that is if you have a set 1 and then 1.5, 1.6, 1.7, 1.8, 1.9 and then 1.99, 1.99 and then 1.9. Okay. What is the maximum of this set?
1.9999.
And what will be the supremum? Supremum would be 2. That is the difference between maximum and supremum. Essentially, the difference is supremum may not be attained. If you call a quantity to be the maximum, then that particular element has to be included in that set. But supremum may not be included in the set, it is going to be achieved. That is also.
So supremum can be outside of the sequence.
Then supremum or the infimum, for both of them the same concept. Here, if you see this series or if you see the pattern, ultimately this is going to stop at 2.0000, but that is, it is going towards that, but that particular element is not included. So the supremum of this set is 2.000, that is the supremum, but it is not attained. So in such cases, if you have to write down the maximum, then definitely we cannot write in terms of max, you have to write sup. So that's why I said, in this case here, we don't have any stochastic thing. Everything, it is first of all finite dimensional, that means a number of elements is a finite number and everything is defined. It is not like a series, not like a sequence. So that's why we are not learning at this moment. Here everything is finite and everything is well defined. For them, maximum and supremum will give you the same. So for such a series, usually or for such a set, usually we don't write max. We don't write. Because this is continuously increasing. If you apply the limiting value, then only you will be getting 2. So after 2, it won't further increase. So that 2 is the supremum. Okay? That is the reference. So the same thing is the infimum versus minimum. Like when we take the series 1 by n. This is a series. And here the n start from all natural numbers, that is 1, 2, up to. Then it starts from 1, then half, 1/3, 1/4. If somebody asks you what would be the minimum, you cannot write. Actually, you have to then define infimum, and the infimum would be 0. Right? But that element is not included, because if you write down in terms of a sequence, it will keep on right going. That is 1/2, 1/3, 1/4. In that way, it will keep on going, right? So the infimum, which is 0, is not attained. So that's why there is, in this case, we cannot write what is the minimum of that set or what is the minimum of that sequence. There we write infimum. That is the difference. Okay. eigenvalue. I don't know that is in which sense you have correlated this with that. So in this case, what is our one norm? So it will be 1 plus 2 plus 0 plus 4. So it is 7, right? Now suppose like sometimes we unknowingly make a mistake. If this is minus 4, then what will be, then also it will be the same. But that is the reason why we consider the absolute value. So don't get confused if you see some of the negative elements. Okay? Is that fine? So for vectors we have only take these 3 norms. Now in between like someone can define like 3 norms, 4 norms, but usually those kind of lengths we generally don't use. Although mathematically all those definitions they exist, but the norms which mostly we use, they are 1, 2 and infinity or the sup norm. Okay? So those 3 we use in different applications or in different analysis. So that's why every now and then we keep talking about that, and that is the reason why every book, if you see the appendix in all the control books, they are usually defined, but not the other norms like 3, 4, 5, so on so forth. Those are not like separately they are mentioned. Why? Because we generally don't use them. Okay. Like those who have read probability and statistics, there we have different type of distances, right? Do any one of you had probability statistics?
We had estimation, not.
So have you heard about that Manhattan distance, Mahalanobis distance? Different kind of distances that is we have in the probability that are different based on different measures.
Statistics.
One norm is the Manhattan distance.
Mm-hmm.
One norm is the Manhattan distance.
That I cannot say exactly at this moment, but they based on different measures they have different type of distances. Now depending upon a particular mathematical application, they bring in that is which one to be like the most appropriate.
So in machine learning also these are used.
In machine learning
Yeah,
also we
yes.
use different type of distances, right? Those things actually come from measure theory. Actually, we don't have the measure theory. That's the problem. Anyways, after vector, then matrix, right? Let us take a matrix. The discussion on eigenvalue, eigenvectors, or even SVD, that is really interesting. So if we someday take a class on linear algebra, then you will find like so many doubts will come up. Now for the matrix, if it is for the matrix, what are the usual norms? One by one, tell me.
Frobenius.
One.
Frobenius will come later. That is, first let us start with here. One norm means it will be the summation norm, right? So in case of a matrix, what is the summation norm? The summation of the absolute values of all the elements, right? So if I write, then is here usually we write in terms of sum norm. So if it is sum norm, then that is it is summation over I comma j aij. You can write in terms of two summation notations as well. That is one summation for I, another summation for j. Here just it is a shorthand. One summation I comma j. That means of course over the all rows and columns. Okay. Overall, this is the sum norm. Are you going to define any other matrix? No, it seems so.
Let me see.
No, you know, like sometimes the while thinking it works, but not always.
So actually it is there. So when like we find out the condition number, we divide the largest like sigma 1.
Condition number.
Yeah. So then we-
sigma max by sigma min.
Yes, sir. So
Yeah.
in some books they write sigma supremum by sigma infimum.
Infimum.
Achha.
See, my junior is that.
That's really good.
That is really good.
We will see. I never said that it was incorrect. I said that I never heard of it.
I have seen it, but I didn't have any point to defend you. So now,
You can't memorize, right? sometimes I can't also recall. We all like.
We are getting old, na?
Huh.
These people are kids.
93.
I am 37.
I'm closer to you than them.
Hey, somehow we have to manage. That is, if not automatically, then we'll have to take some help like Brenoria and other kind of syrup.
Brain implant. Brain transplant.
Or even an artificial intelligent brain. Anyway, then after some norm, then.
Norm 2 is
But in case of matrix 2 norm means that is also called the spectral norm. Spectral norm, the definition is little bit different. So I am coming to spectral norm. And then that is after some norm.
inferior norm.
Exactly. Infinity, or rather this is called the max, right? Infinity or max. In that case, how would you write? That is again maximum over I comma j. Exactly in this way.
Max element of the matrix.
Exactly. And later you will find that for these norms, for except that norm, because you might have heard there is this norm, they satisfy the norm inequality, right? That is norm of a plus b, triangular inequality. That is usually for most of the norms they find they satisfy. That is a very useful property. That is called triangular inequality of the norms. But in case of matrix, I think the maximum norm, it doesn't satisfy that inequality. I have to check the list. I have also forgotten. But don't worry, all these properties, even some of the examples, they are given in the appendix of Skogestad book. That is the reason why last day I mentioned, maybe last day or last to last, that is please check the appendix from Skogestad book. Okay? क्या हुआ? Any doubt?
Website थी ना
Oh, acha. That all of you had that book, right? Multivariable feedback and design. So if you see, if you go to the end, it has a very rich appendix where all the norm definitions and the properties, identities, inequalities, everything is mentioned. Okay. So then after sum and then the big value, what else? Infinity or maximum, same. And then that is any other than?
Row और column को भी separate होता है max of row और
that वो भी होता है. जैसे for a matrix, that is a maximum of the row sum, a maximum of the column sum, isn't it? That is also, but usually we don't use those things. So that's why if you see that book, they have defined 6 matrix norms, but usually we don't need that many. For a matrix, is usually sometimes we need some because it is some sense related to trace of a matrix. Then sometimes we need that infinity norm, mostly the spectral norm, which is also the 2 norm. Okay, and in some cases Frobenius norm as well. But that the row sum norm, column sum norm, that is also there. Although that in control we don't use that much. If you wish to see the appendix just to get familiarized, you can open. If you have internet access, please that is open the PDF. that was for Kemin Chow, even like that is not the Skogestad book. Monica, you never downloaded that book?
No, I have that one like you said.
It was in Outlook.
Oh, मैंने
तो तुमने बुक देखा पहले?
वो नहीं दूसरा वाला बुक देखा
दूसरा वाला मतलब?
जो आपने PDF सेंड किया था हाँ
बट वो तो मैं Skogestad का बुक से प्रीरिक्विजिट में पढ़ने के लिए बोला था ना, चैप्टर 2, 3, 4.
वो मेरे लैपटॉप पे है
अच्छा.
वो बुक मैंने देखा
Now you see, 2 norm means it is actually the gain provided by a matrix. What is the concept? Let's say that is you have a system, a static system. G is a matrix, okay? Then output means that is y equals to this gain into, or even this matrix into the input, here in y. That is equals to G into U. Now, how much is the amplification of U? That is basically the norm. Are you getting? That is, if you have output equals to that system function into the input, and then if somebody asks you that is ये जो output ये input का कितना times है, then that is the concept of norm. So in that way, we define the 2 norm of a matrix. That is it is a matrix 2 norm. Here we write the vector 2 norm of the output by vector 2 norm of the input. Okay, that is the concept. We start with this, but here we have a problem. That is, if we have to formalize it, then the input can be of infinite choice. Then every time we have to like check, we have to find that ratio. Although that is, if it is a like linear system, not linear, that if it is a linear system, you will find that is the gain, or if it is not only linear, suppose if it is constant matrix, then the gain will always be same. But if it is a frequency dependent matrix, then depending upon the frequency, the gain will also be different, as the case for transfer function. Okay. So here what I wanted to mean, that is, if it is vector 2 norm of the output, the ratio of the 2 norm of the output to the 2 norm of the input, then if the input it keep on changing, then output will also keep on changing. Then how many times you will just keep on finding the norm, right? So if we can restrict this, like suppose if we can conduct this experiment over all possible inputs whose 2 norm is 1, then it would be much easier for us to find the gain, right? That means suppose the testing is over something like that, then all the inputs, either you use the scale version of the inputs or only the class of inputs whose 2 norm is 1. If it is so, then that is, if it is so, then what will you do? That is, in place of y, you can write ax and then over x, okay? And then what we do? In this way, we define the matrix 2. Okay? Basically the gain norm, and usually exactly in the same concept, if you, that is, instead of this G, it is a constant matrix, if you consider it is a transfer function matrix, so there you will see that this matrix 2 norm will finally lead to that infinity norm in case of a transfer function. At this moment, that is, you may have a slight doubt, that is what we are defining, it's a matrix 2 norm, but the moment what I just said, that is, if it is G of S, and suppose this is Y of S and this is U of S, and then this will resemble here you have a type. Like in case of matrix, this is a 2 norm. But I said that in case of transfer function matrix, the same concept, but it would be the in system norm, but not system 2 norm, system infinity norm, right? Here you will have a slight difficulty that we will discuss later. Why I said that it will resemble, because here also you could see this is a ratio of the input to output, that's why it is giving a gain, right? And infinity norm, we have already learned the infinity norm, that too, that is that is it is the ratio, it is giving you gain, right? So in that sense, both of them actually gives you gain. So the matrix 2 norm and system infinity norm, both of them give you gain. But so that's what I said, that is you may have only this doubt, that is then why is it not 2? If it is matrix 2 norm, it could have been system 2 norm as well, but why it is infinity? That doubt we will discuss, okay? But anyway, at this moment I am not going to system norm, let us finish this one. So for the 2 norm, that what we have already, maximum over x or u, whatever you write, equals to 1. So have you understood this standardization process? That is why we are taking that input signal to have, that is 1 norm. Otherwise, that is if you don't restrict the input, then for infinite choices of input, every time you have to keep on finding that again. Okay, that's why that is like this. We have to reduce this denominator. Okay, that is the choice of the input. But that is not the end. We still have the problem that here how would you actually find? So this can be like proved that this will be sigma max of A, or even it will be square root of lambda max of A transpose A, same as lambda max of A transpose, isn't it? That you know, that is can be found. That means this is the very easy process to calculate. That is, now at this moment we are not going into the proof, but all the, that is the norms and everything, they have their proof, and that actually for that, if you wish to see the proof, I can give you the reference. At this moment I am not doing, because this proof they require certain knowledge from functional analysis. So those things are actually not there. If we have to teach, I'll have to first cover many of the prerequisites. That's why I'm writing only the formula. But I can provide you all the materials, you just have a look. Then it will be more interesting. So this 2 norm, it can be calculated by using the sigma max, okay, and which is square root of lambda max of A transpose A, and then which is the same as lambda max of A transpose. Okay, they will be the same. Now from that, if you are a beginner, you might have a doubt. Then is it does it imply that is A transpose equals to A transpose A?
Eigenvalues stay same.
Eigenvalues will remain the same, but of course they are not the same, right? If A is a non-square matrix, then because like this nowhere I mentioned, although that for this example it is a square one, but when we define the norms, then they are not for the square ones, right? Just a second. So all the norms, like they are defined for the square and non-square matrices. So if suppose if A is non-square, then A transpose A and A transpose, they are not the same, right? But they have one unique relation, or some of the features are common. What are they? non-zero eigenvalues will remain the same because number of zero eigenvalues will be different. Are you getting why? What did I say? That is, if we let's work with non-zero if we work with non-square matrices, then what would be the common in between A transpose A and A transpose? The non-zero eigenvalues will remain the same, but not the zero eigenvalues. Let's say that is, you have this example. This is suppose A. We are taking a fat matrix. Okay. You calculate this one and then what will be the situation?
One is a 3 cross 3 and
First one is 2 plus 2. First one is 2 plus 2. Second one is 3 plus 3.
So in this case, what will be the dimension? 2 cross 2. In this case, what will be the dimension? Right? In this case, can anybody tell me that is how many zero eigenvalues would be there without calculating?
1.
1. Why?
Second one is scalar multiple of the first one.
Then what did Nidisha? In this case, how many zero eigenvalues?
1 because it is number of rows will be checking with number of unknowns with number of rank with a number of unknowns.
ठीक से बोलो, सोच के बोलो. Everybody please think about the reason. कनिका तुम भी सोच के बोलो. जो इधर number of zero eigenvalues एक होगा, but why?
rank is 1.
रैंक
Independent
और
vector thing is
एक ही होगा, रैंक 1 होगा ना, रिड्यूस हो गया ना उसका, इसका क्या बोलते हैं, एक रो रिड्यूस हो गया ना, एक पहले राइट ए ट्रांसपोज का 3 रो था, एक रिड्यूस हो गया, तो रैंक डेफिसिट हो गया, रैंक डेफिसिट होने में एक रो आइडेंटिटी आ जाएगा.
Sir, sir, in two ways we can understand this. In the right side, the A transpose matrix, it spans a 3D space. And when we are multiplying it with a matrix that is spanning a 2D space, so one direction will get collapsed. So
But even easier than that, how can you decide the rank of a matrix?
So by solving it and then finding out that one row is independent, dependent on the other.
And in that now you have a product of matrices, right? And then there is we are talking about the rank. In a very simple manner, how can you judge it? Let A belong to M cross N. Then rank of A is lesser than equals to
Max.
minimum of
Minimum.
N comma N. That is the most useful rule, which would be required here. So then ultimately what is happening, that is you now, that is what you have to, what you are trying to get here, the rank of A transpose, right? If that is A and that is A transpose, now like first of all you decide what is the rank of A. Here, like everybody please look into the board, that is here A is a fat matrix. For a fat matrix, what could be the maximum rank? That is,
number of
Number
rows.
of
I said that is what could be the maximum rank. Number of rows, but now here it has 2 rows, but we can easily check. That is, the rows are not linearly independent. The second one is a scalar multiple of the first one, right? So in this case here, what is the rank of that matrix? 1. Now, that is after that, if you have to decide the rank of A into A transpose, then that is already, that is its rank is already, that is A, the rank of A is 1.